There we go. So let's do this. Okay, so let me introduce myself. My name is Adam Hibbert, and I worked on the Ariane 4 project, which is a launch vehicle whose final flight was in 2003, so quite a while back. And I was kind of a guidance expert, so I worked on the guidance algorithm. But in 2017, I came back to software engineering. And I decided to develop some software which I called Optimum Interplanetary Trajectory software. And this was a challenge for myself to learn the MATLAB language. And MATLAB is a software language. And if you know anything about software, it's got an integrated development environment. So it's kind of software application that allows you to write software applications. So I developed a theory behind this interplanetary trajectory software, and essentially what it does, it allows you to design missions to the planets or other celestial bodies in the solar system. And that might entail a series of gravitational assists, for example, or it might just be direct from one planet to another planet. And I used it, eventually I used it to study missions to an object called Oumuamua, which Mark described briefly at the beginning. So we'll get onto that in due course. But first of all, I'd like to introduce how you might use the software. It's available on GitHub, so there's a software repository, so you'd be able to download it onto your own computer, potentially, if you wanted to, but you'd have to have the MATLAB integrated development environment, and that costs quite a bit. So, but I'll show you how to use it anyway. Let's try and reproduce, for starters, a mission called Mars Insight Lander. And this was a NASA mission which launched in 2018. And we want to try and reproduce the trajectory using OITS. Let's have a look at this, how we might go about doing that. So what we do is open up the integrated development environment, and then we type run_OITS and then return. And you get this, and you get a menu, as you can see in the middle there. That's the middle rectangle. And you've got a series of options there. So you can open mission, view missions, save missions, etc., etc., etc. We'll come on to those in due course. What we want to do is start a new mission. So let's click on new mission. So I'll do that now. Okay, here goes, new mission. So what we have then is a drop-down box on the left. So we can select from a series of planets. And you've got Neptune there and what have you. You want to start off at Earth, obviously. And further down, you might see Oumuamua. So we'll come into that later, as I say. And you also have intermediate point, and I'll explain what that is in due course as well. But for the time being, we want to start, it's asking us to select body number 1. So we select Earth, naturally, and then we select Mars as body number 2. So let's do that. Oops, I've gone too far. So as you can see, Earth and Mars have appeared on the right-hand side there. And it's asking us to select body number 3, and we don't want to go to a third body. We're just happy to arrive at Mars. And so let's now continue. So go back to the main menu, okay? Quit selection. Now, I've entered an arbitrary mission name and Mars_mission, okay? And all the software knows at the moment is that we want to go from Earth to Mars. Now, if you know anything about your space astrodynamics, then you know that the planets go around in orbits, elliptical orbits generally, around the sun. And there are periodical optimus trajectory from Earth to Mars. So there's a kind of something called the, there are periodic trajectories from Earth to Mars, essentially. The synodic period is the word I was looking for, apologies. So synodic period, so every synodic period there will be optimal trajectory from Earth to Mars. So we want to constrain our search space so we look within a certain time period, okay. So let's set optimizer details, and we come onto this table here, okay, and we have at the top, we have Earth. So this is trajectory pertaining to Earth, and I'll start up my microscope here so we can have a look in detail. Hopefully I'll start our microscope, there we go. So you see at the top we have Earth. So this is all data pertaining to Earth, that's the blue row, and the second row is Mars, and that's all data pertaining to Mars. And it's asking us to select a minimum launch date, and that's 2018, January the 1st. I've selected, I've already entered that data. And we're going to end, the latest launch date is going to be 2019, January the 1st. And if you remember, Mars Insight Lander, it launched in 2018. So our software, my software, is going to look somewhere within 2018 for the best launch date for getting to Mars. And then that 10 there in the Mars row is kind of the minimum number of days it's going to take to get from Earth to Mars, okay? So it's going to take at least 10 days to get there, and maximum 500 days to get there, okay? So let's move on, and let's come down here, and I've checked this rendezvous with destination box. Now, what's that all about? Well, once we arrive at Mars, we've got two options. We carry on in the direction we sort of arrived in, so we can continue going in the direction we were traveling when we arrived, or we kind of slow down. We try and apply a burn or a thrust using our onboard engines to stay with Mars in its orbit around the sun. Now, if you know Mars Insight Lander, that sort of did the latter. So we want to stay with Mars. So we want to slow down at Mars to make sure that we stay with, so sort of stay abreast with Mars as it orbits the sun. Okay. Then we have this data here, minimum periapsis. So what's all this? So I've selected 200 kilometers for Earth and 200 kilometers for Mars. And what that means is that we're starting off in a circular orbit around Earth of 200 kilometer altitude. Okay. And when we arrive at Mars, when we apply that burn to slow down, to rendezvous with it, that's going to be at an altitude of 200 kilometers too. Okay, so we've selected all this data, and so we kind of can now run the optimizer and see what trajectory it comes up with. Okay, so let me just close this magnifying glass. Let's go, and I've selected run optimization, which is another option available to us. And what happens is there's a list of numbers. The numbers scroll down, as you can see in this box here. And what those numbers represent is delta V. Now, what is delta V? It's kind of a measure, if you like. It's a metric of the trajectory. It's a kind of measure of how much mass, fuel mass is needed to get from Earth to Mars. And we want to minimize that fuel mass because we want to maximize the useful payload mass, which are things like power generators, or solar panels, or it may be high gain antennas, or whatever instrumentation you may need to analyze Mars when you get there. So we want to minimize the fuel usage. We want to minimize its delta V, and that's what the software does. It tries to minimize its velocity increment, if you like, to minimize the fuel mass needed to get to Mars. So having performed this calculation and come up with an optimal trajectory, it's optimal interplanetary trajectory software, yes. We then select view results. So let's view results now. And we get this table here. I'm going to open up the magnifying glass, so bear with me. And we see on the top row, Earth data, and the second row, we've got Mars data, okay. And we have the optimal launch date here of May the 11th, 2018. And we've got the arrival date is December the 1st, 2018 at Mars, okay. And we go to the right here. We've got cumulative delta V. Now, this is the delta V I was talking about that the software was trying to reduce to as minimal value as possible, lower value as possible. And it's come up with 4,403 meters per second. And that's 4.4 kilometers per second. So bear that in mind. That's the lowest delta V it came up with. And also the delta V at that circular orbit altitude above Earth's surface, of 200 kilometers above Earth's surface, that delta V was 3.57 kilometers per second, and it arrived, the delta V to slow down at Mars was 828.7 meters per second. Now, having achieved these results, having acquired these results, we need to compare them with the true results that NASA came up with. But for the moment, let's have a look at the simulation, an animation of the software, of the trajectory rather. So let's do that. So let's select animate results, okay, and we get this. It's an animation of the trajectory. As you see, the red dot is a spacecraft, and the inner circle is Earth's orbit, and the outer circle is Mars orbit. And that's what it looks like. That's what the trajectory looks like. That's the solution that OITS has come up with within that search space that we constrained the search space, as I say. So let's have a look and compare that with a NASA mission, okay. So what we have here, I'll open up the magnifying glass again. We have NASA Trajectory Browser. Now, what that is it's an online database of all the trajectories that NASA has come up with from Earth to the planets and celestial bodies within the solar system. So you can access this NASA Trajectory Browser and search for missions from Earth to Mars, for example, and you can see what trajectories NASA has come up with. So that's what I've done here. And what we find is this mission here. What we see is that the total delta V there, that's the velocity increment I was talking about, is 4.36 kilometers per second. And that compares rather favorably with the value that OITS came up with there, which is 4.4 kilometers per second. I hope you can see that. The delta V required at Mars is 821 meters per second, and that compares well with the delta V that OITS came up with, 828 meters per second. So we seem to have a fairly accurate solution here, which seems to compare quite well with what NASA came up with. Okay, so let's move on to a different mission now. Okay, we've done Earth, Mars, let's go on to a different mission. So let's go on to, for example, New Horizons. Now, if you know New Horizons, that's the mission to Pluto. And that incorporated a gravitational assist of Jupiter. So it wasn't direct from Earth to Pluto. It went to Earth, to Jupiter, and then Jupiter to Pluto, and used the gravitational assist of Jupiter to reduce that velocity increment needed to get to Pluto. Now, that's the delta V I was talking about. Now, the launch of New Horizons was in 2006. So we're going to try and reproduce this mission using OITS, as I say. Now, that velocity increment, if you think about it, the lower the delta V that is required to get from Earth to Pluto, the longer the travel time it will take to get to Pluto. So in other words, you could have infinitely long durations and lower delta Vs. So OITS tries to minimize the delta V. So if you don't set a limit to the duration, then it could last for thousands, millennia, it could last forever before we get to Pluto. So you must constrain the mission duration to 9.5 years, which is the value that NASA selected for this Horizons mission. So let's try and reproduce this using OITS, as we did with the Mars InSight lander. And I've selected the optimizer trajectory, optimizer details rather. And we have on the top row got Earth. So this is the blue row here. Again, we're starting off at Earth. And New Horizons was launched in 2006. So it's got an earliest launch date of 2006 January the 1st, and the latest launch date of 2007 January the 1st. So it's going to look throughout 2006 for the optimal launch date. From Earth to Jupiter, Jupiter is going to take at least 10 days at the maximum 2,000 days. And from Jupiter to Pluto, it's going to take at least 100 days at the maximum 100,000 days. But the important thing is that we've constrained the mission duration to be less than 9.5 years, which is approximately what NASA chose for this mission. And we've got various information like, for example, these periapsis altitudes here. We're going to start off in a circular orbit around Earth of altitude 200 kilometers. And we're not going to get any closer to Jupiter than 200 kilometers. That's because we don't want to run the risk of colliding into Jupiter and end the entire mission. So we want to constrain the periapsis altitude to be larger than 200 kilometers. And in fact, the solution is much larger than 200 kilometers. So we're fairly safe. So let's have a look at the trajectory that OITS then comes up with, shall we? So let's go on to the next slide. And to the lower right here, this is OITS data. This is the solution that OITS came up with. And instead of clicking on, using NASA Trajectory Browser, which I did for Mars InSight Lander, I've got the real mission from Wikipedia. So we can compare with the real mission, okay. So the top row is 2006 January the 20th, and that's the Earth launch date, okay. And we get for the real mission, yet the launch date is January the 19th, 2006. So we're one day out. Then 2007, March 1st is when we encountered Jupiter. And it's February the 28th, 2007. So we're one day out again. But Pluto arrival time, 2015, July the 20th. And we arrive at Pluto July the 14th, 2015, which is how many days out? 6 days out. So in other words, what NASA did was use a different mission duration than to the one I used. I used 9.5 years. They used a slightly different mission duration. But this periapsis altitude here is 2.26731.8 kilometers. So it's about 2.3 million kilometers. That's how close it got to Jupiter, rather. And that compares favorably with the actual distance it got from Jupiter, which was 2.3 million kilometers. So we're doing quite well, I think, OITS.